Hey, everybody. Thanks for joining this talk. Today, we're going to be talking about Liqid's CDI architecture and how it can be used for data processing, really, in the HPC and the computational science space. My name is Josiah Clark. I serve as the Chief AI Architect at Liqid. Mostly what that means is I spend a lot of time designing hardware architectures for computationally intensive workloads. Prior to Liqid, I've spent about 15 years building applications that take advantage of machine learning mostly, which include large-scale HPC systems. I didn't start in hardware. I started as a computational scientist, and as we all probably know, or as you all probably know, very quickly, the computer, the physical hardware becomes the bottleneck in a lot of the stuff you want to do. So that led me into the hardware space, and where I kind of split my time today between algorithm development and developing new hardware platforms to basically get my job done faster. So hopefully this presentation will be helpful for you. So I'm going to start off just with what is CDI. So a lot of you might not have heard about the term CDI. CDI basically stands for Composable Disaggregated Infrastructure. So what that means is if you think of a traditional hardware, server, compute, storage infrastructure, we have, you have the box, and in order to split up the resources in the box, we have things like virtualization that allows us to actually carve up resources, things like containerization that enable us to carve up workloads and containerize them, so we can run different, libraries and things like that on the same machine without interfering with another application's configuration and package stack. And then we have things like bursting to the cloud, which is pretty nice. With on-prem infrastructure as a service that allows you to do cloud-like orchestration, but and burst into the cloud when you need to. The problem that, all of these kind of have is they're still limited to the physical infrastructure of a server. So, these little stacks of compute, storage, GPU, networking, it's all based on like an individual building block. And every year there's only a couple hundred different building blocks that are out there. And they're not bad, but as we all know, in the computational sciences space, there's every different algorithm has kind of a different sweet spot, and there's, literally, trillions of different combinations of these devices that could, end up being the sweet spot for your device, but we're limited to equipment that's stuck in servers. So what CDI does is it basically takes all those resources from the different hosts, and we actually pull them out of the servers physically, and we insert them into pools. So kind of like how we do storage today with like enterprise storage systems, but we do this for GPUs, network interfaces like HCAs such as ConnectX-6s, ConnectX-5s, all our high bandwidth network interconnects, as well as our high performance storage. So this is PCIe storage, Optane storage, SSDs, things like that. The stuff that you'd usually stick inside your server as close to the CPU as possible, in order to, not have anything between you and that very fast storage. So we pull all of that out and we stick it on a PCIe bus that is not inside the server. And that enables us to compose servers using this thing called, our Liqid Matrix software. But it allows us to compose the servers based on the job we need. So, fundamentally at a logical level, we can take a CPU, a fast SSD, a couple GPUs, and then we compose a storage with the physical hardware resources without impacting the performance. So you have the same performance that you would have with a bare metal server. And then you can create another node and just basically kind of mix and match and create your nodes based on your workload requirements. So the building blocks of this technology are our Liqid Command Center, the Liqid Matrix, which is just a software application. We have a physical PCIe switch. So instead of like all of this being on a PCB, the switch that ties all this together is this physical device. And then you just add in expansion chassis for FPGAs, GPU, storage, compute, coprocessors, HCAs, however you want. And then you compose the storage configuration that you need. And then lastly, you connect it to, say, like some pizza boxes or some high density nodes, because we do not compose CPU. So Liqid doesn't do that. Then, if you want to throw in like Optane or some new requirement comes up, you can just drop it in another shelf and connect it in, and now your architecture has a Optane memory. So there's a couple different ways to control all this technology. I'm not really going into a lot of this, but it's kind of important for this talk since it's storage based. So there's a couple different ways to compose the servers. What I like to use is job schedulers or Kubernetes personally, because that way, probably because that's what I'm used to using, but also I can control not only the job, but the hardware that's going to be assigned to that job and the type of server that I want to create dynamically. And I just schedule it all and run my jobs, and the system creates what I want. You can do it manually, and you can also interface. There's a JSON, or excuse me, a REST API that takes like JSON files that you can just say, hey, create this, what I want. But I do a lot of stuff with like same data sets. So I like to use gang scheduling and stuff like that Kubernetes has, and Slurm has as part of it. So that's kind of helpful when I'm working from a data perspective. So usually I will be found working with Slurm or Kubernetes, but you can, kind of do this however you want based on what you're using in-house. So another thing that we kind of do that's a little unique, that some of the stuff I'm going to talk about won't really make sense unless I go over it, is our peer-to-peer optimization. So basically, between GPUs and GPUs, or coprocessors and coprocessors, most of the computation and on data that occurs between devices, or really it's memory copies between devices that's happening, it happens all over via DMA. And hopefully it should be, as long as you have your system configured. Sometimes it might not be, but as long as you have the right plugins and drivers and stuff installed and libraries, you should be ideally, if it's a PCIe device, you should be going using DMA and going device to device as fast as possible. Now, DMAs allow us to avoid the additional mem copies of going into main system memory and out of main system memory, which is why we all use that, right? But the data still has to traverse the PCIe bus, which is traditionally in a tree structure. And if the devices need to communicate with each other, say one is on one CPU 1, the other's on CPU 0, then what can happen is a bottleneck can occur at the XGMI interconnect using AMD, or the QPI interconnect if you're using Intel-based servers. So basically, it's like this known bottleneck, and you definitely run into it when you're building HPC systems and you're doing a lot of DMAs between different systems. We bypass that since we are extending to PCIe bus. We actually add these bridges at a lower level, and then we route traffic across those, so you don't have to end up going all the way back to the root complex, and there's substantial performance benefits. So just to kind of like depict what I'm talking about here. So with a typical, so let's say we have storage, the data that needs to be read from this SSD to this GPU using something like GPU Direct. It flows up into the CPU, back to the root complex, and back down to the GPU. And there's some latency that's injected there. Now, using the Liqid architecture, the matrix architecture, basically that same operation can occur, except instead of having it to go all the way back to the root complex, it just goes back to our bridge here in our PCIe fabric. It's pretty much transparent to the user. You don't need to turn it on or anything. It just happens. So basically, this is just an example, GPU to GPU, peer-to-peer communication between two GPUs, saying like an ML model during the all reduce step. This is pretty much a requirement. So on the left, you see the non peer-to-peer enabled, so the peer-to-peer disabled version, and then on the right, you see the peer-to-peer enabled feature. And really, it's about 400 or 4x to 5x the performance of the non-peer-to-peer version, and latency is much less because we're not doing those protocol translations, which is a little non-intuitive. But if you think about it, you got to go into XGMI, and there's some sort of protocol translation when you hop across CPUs. So we don't have to worry about that. So it scales really well. These are just some more fun performance slides from a marketing perspective. I'm not really going to go too much into these. The short part of it is it's pretty fast. So this also works for GPU direct technology. Here we've got some GPUs, reaching out to local storage. This also would work for things like Magnum IO, GPU direct. These don't have to be disks. These could be HCAs going back to your, DDN cluster, your Isilon, or really any storage system that supports Magnum IO and GPU direct. Assuming these are like NVIDIA GPUs. So I'm not going to go into this too much, but basically, in short, it's just a lot more efficient. Okay, so now that I got over what Liqid does, so how does this actually apply to a storage environment? So if you look at the traditional compute architectures that are used in computational biology or HPC in general, we really kind of have three main kind of macro level architecture. So we have a shared storage architecture. You've got your compute nodes. This is the one on the left, and you've got some sort of shared storage cluster. So it could be like a Lustre cluster, a GPFS cluster, or it could be just like an S3 bucket or something. But the reality is all the nodes connect down here and they use the storage. Next, you have your Scratch-based version, and I guess one thing is naturally a lot of these exist concurrently. So a lot of times you have Scratch-based, but just to keep these diagrams really simple and clean, I broke them out. So you got your Scratch-based, and basically that means each node has usually a high performance storage device on it. This could be PCIe storage. This could be just straight up a bunch of NVMe drives and a software RAID 0 using something like MD80M. But it's just a place to do things like ETL and write calculation outputs and things like that are large. Or maybe even pull a data set off of the NAS or parallel file system and then start working on it. And actually, this is kind of probably the most prevalent architecture that's used today in deep learning, where you have a shared storage space and then this Scratch disk. Next, we have data sharding. This is probably used a little bit less in traditional research environments, just because there's an assumption that you'll have a data set, you chop it up into n shards, you spread those shards across all your compute nodes, and then each compute node kind of works on its own little piece of the problem, and that way you avoid moving things around. So if you have a large biometrics data set or genomics data set that's very, very large, and you know that your type of calculation or computation can be sharded easily, a lot of times this avoids the reading and constant reading and writing from a shared storage system to the local storage. So those warm up times are reduced for running a large algorithm. Really works best for very, very large data sets. And the larger the data set becomes, this is kind of what we see. Very prevalent in the hyperscale space. Companies like Google and stuff like that, who are just sucking down tons and tons of data, they've kind of optimized this a lot. Haven't seen a lot in the deep learning space, and that's, I think, is due to the high churn rate of the algorithms. New stuff is coming out constantly, and data sets are just increasing in size and really quality. So, but these are kind of the three major storage architectures we find in our world. So the downsides, which we all kind of gotten used to this, they're not necessarily bad things. They just are kind of the things that limit some of the performance. With shared storage, there's fixed bandwidth per node. So you buy a server, you stick an HCA in it, you have only a certain number of HCAs you can stick in that, and you can't change that. Bandwidth is fixed. So we kind of build these things on a multi-year cycle where we're all right, this thing's going to get 50 gigabytes. I'm going to stick 2 ConnectX-6s in it, and this will be that's just the bandwidth between the node and the storage, storage system. And then when the new system comes out, we connect X7, we got to do a monolithic upgrade, and just buy new servers, find a new server, and do that. And if I have I have like some node for some reason that could benefit from more bandwidth, like adding HCAs, usually you can't dynamically do that. You have to just go add it. You have to go buy another server. So in the scratch space world, like one of the big problems I've run into is, so like if you have J jobs that require the same data set, you tell your scheduler to go do that, go run all those different jobs. What can often happen is you need to do J, for the, basically you need to load the data for the same amount of times as you do. Basically, the number of times you have to load the data equals the number of jobs. You can get around this with gang scheduling, but it doesn't. Basically, the same job has to be run on like the same node. So, like if I had multiple jobs, one required a high memory node, and one of the jobs required like a GPU node. Even though the data is on, let's say that starts on the memory node, if I'd like to move it to the GPU node, I have to still do that copy. So it's like, stuck. So, and then you can't expand your scratch space very easily, definitely not dynamically. You've got to go buy new hard drives or SSDs or whatever to do that. And usually that's done at server upgrade time. So data sharding has some similar performance implications as the sharding or the scratch disk approach. You can't really move data between node types. If you want to, it's like the shard lives on the server. That's kind of the whole concept. And when you want to increase the capacity of your shard, you usually have to go buy new servers or buy new SSD. So you can't. Things are not as dynamic. Okay. So let's break these. I'm just going to break these down and show how Liqid's technology addresses these, kind of limitations that we see with these, these three, high-level storage architectures that are commonly seen in HPC and computationally intensive environments. So the first one we're going to start with is just the shared storage space, shared storage limitations, because most of us all are using some sort of a shared storage system. So here we have, a cluster of nodes, of compute nodes. Those are the green boxes. We have Liqid CDI infrastructure. Each node has, let's just say, one HCA assigned to it, and those HCAs connect to shared storage. Now, these could be any HCA. You could be using stuff from companies like Chelsea or Mellanox or Arista or whatever. It doesn't really matter. It's as long as it's a PCIe device. And, they're serving up whatever data is contained on this shared storage system. So let's say one of your jobs for some reason could benefit from a much larger data set, or much larger bandwidth. With typical infrastructure, you're stuck. It's just like too bad. You'll have to just wait. With Liqid, as long as these HCAs aren't being utilized or scheduled, or maybe if it's more optimal to load all this data quickly onto compute node 2, you can just reassign the HCAs to compute node 2, and then they get all the bandwidth, they load the data, and then they're off to the races. So Liqid's technology addresses that ability to assign HCAs, thus increasing the bandwidth to a single node or different nodes, however you want. Secondly, when new HCAs come out that are a little bit faster, we just saw this happen with Connect X5 to Connect X6s. It's very easy to just add that HBA into the Liqid CDI infrastructure and then assign it to the node that's capable of taking advantage of that network. Okay, let's talk about a little bit about scratch space. So with scratch space, we kind of talked about that. You load your data set onto your server, local storage. Again, we have our 4 nodes here. We've got SSDs and the Liqid CDI infrastructure. And usually a scratch space, there's a shared storage system of some sort where your data sets live. So let's just say we kick off a job on node 1. We move the data set up to node 1, and it starts working on it. The job is complete. And then node 2, suddenly, that job finishes up and a job is scheduled on node 2. Node 2 happens to need that same data set. So all Liqid has to do is the job profile, and Slurm would have to say, hey, take the scratch disk that is being used for node 1, map it to node 2, and mount the volume, and start working on the data. So this prevents that secondary read operation and the write operation to your system, which saves you time and resources, both on your parallel file system as well as on your scratch resources, and reduces the warm-up time as well. The next use case is, well, what if you have a very large data set? Someone comes in and says, hey, this is really amazing. We kind of saw this with COVID, when all of a sudden, something unforeseen happened, and there were all these data sets that were available, and our systems weren't designed necessarily for those new data sets. We didn't know they were coming. And some systems had scratch spaces that were a terabyte or something and weren't large enough. Well, with Liqid, all you have to do is you just say, hey, I'm going to take this scratch space, which is basically an SSD of some sort, and I'm going to map it over here to compute node ... And now I have room to mount the entire data set and on the scratch disk dynamically do my job, and then I can return my resources to the pool. Now, sharding, as I mentioned, it's pretty similar to the use case is similar to scratch spaces. But in this scenario, we have 2 compute node types. So we have got our standard, HPC compute nodes, and then we have some GPU compute nodes. And we also have 2 different data sets. This is very common. You'll end up seeing some shards living on different types of servers that are more optimized to whatever the primary computation or primary shape of the algorithm is that you want to run. So we have data set 1, which is shard 1's 1-1 through 1-2, and then we have the second data set, which is shard 2-1 through 2-2. So let's just say for some reason you want to do a huge ETL job on, let's just say these are the green nodes are your high memory nodes. You don't want to have to move all that data across your system, across your network. Like I mentioned earlier, sharded data sets are very, very large, and that would just be horribly inefficient. So all you would have to do with the Liqid CDI platform is just remap those drives to the other nodes, and do your ETL, and then remap them back to the GPU nodes, and you're off to the races. Next comes to expansion. Well, let's just say that we need, this data set is growing, but the compute, these servers still have enough compute power to process the data. They're not compute bound. It's capacity bound. You're trying to more efficiently utilize your infrastructure. Well, in this case, it's very easy. All you do is, like you saw in that previous slide, you slap in another shelf of Optane or NVMe or whatever your chosen media is, and you non-disruptively increase the storage capacity of those nodes. So fundamentally, this is how these are kind of the methods that you can use Liqid's technology. Liqid is very much a technology. We're not a huge ecosystem company. We don't have some monolithic platform that we're trying to sell. It's just what we see as a better way to enable the community to do or really solve problems in the computational intensive spaces. So I hope you got something out of this. If you're interested in hearing more, I'm the chief architect over here, mostly focused on AI, which has drugged me back into the HPC world. But AI kind of touches everything. So I've dabbled in molecular, generation and novel molecules, generation for the pharmaceutical industry and all sorts of interesting problems. But feel free to reach out to me, josiah.clark@liqid, that's liqid.com. If you have any questions, or our sales team, I think it's sales@liqid.com. Anyway, thanks for the time, and I hope you guys all have a great week, and enjoy the conference. Take care.